Hey, thanks for watching. I'd like to first, kind of explain that this is the first time that Hackers Assembly had did a live stream on Twitch. So there are a couple of glitches in terms of the lighting and perhaps the angle, and also my own personal failure of staying in frame. So the guys are great over there, and I just want to kind of indicate that. So as you're watching, you may want to have the slides, and I am providing the download location for the slides. So once again, thanks for watching, and there's a contact details at the end, so feel free to reach out if you have any questions. Alrighty, enjoy.
Okay, thank you for coming. I think this is technically the first meeting of Hackers Assembly. There was a rename. We were formerly Trash Panda Village. Today we have Ray Garcia with us, Dr. Ray Garcia, talking about using fuzzy logic for security. I could go into more detail, but really I can't speak to it as eloquently as Ray can. So thank you for coming, and enjoy.
That's fine.
Go ahead. I'm sorry about that.
So, anyway, thank you for the kind introduction, Leo. My watch is buzzing for some reason. Anyway, and I know you have to leave soon. So this is kind of a continuation of a talk I gave here in March that went through security and fuzzy being applied to that. And in this case, I'm kind of focusing more on the kind of the streamlined process of applying fuzzy, and then just using a couple of examples. And one is unrelated to security, but it's kind of a bridging example to get people to kind of get this intuitive understanding, and then I apply it to phishing. And in the open source work, there is some updates that were posted today that has an example set up. But this was partly meant to be a workshop as well, so I don't think you'll have time. But did anyone read the kind of the intro and download maybe the GitHub repo? All right, so you guys won't be ready. You did? Oh, okay. You don't have the time, but you were prepared, right?
Yeah.
I got it. All right, well, so the title is Streamlined Fuzzy Inferencing for Anti-Phishing, and just to say it again, the reason why I had it as streamlining is I didn't want to focus on a particular programming language. I didn't really even want to focus on a particular software package. It just so happens I wrote something 8 years ago for applying fuzzy, and it just is only applying to a standard language. There's a standard scripting language, and it's about using the standard fuzzy control language. And that way you can pick any library you want that supports that scripting language. This is one of them. So let's get started.
Here's what I found.
Some of these are going to be from March, so you're not missing much, but the idea is to kind of walk you through fuzzy and get you thinking on how to solve problems that you really have some heuristic for, and there isn't a closed form expression, right? Unlike other algorithms, if you go towards the end of this, I'll have something on the data that I'm using to validate anti-phishing techniques, and you'll see that there are a lot of statistical-based techniques, and you can use neural computation as well. But oftentimes, a lot of these descriptions, for phishing itself are rules, right? A lot of them are rules. If I went through maybe 10 years of papers on looking at how phishing was solved or proposed solutions, and a lot of them are, if you narrow it to web URLs, a lot of that is, looking at the content and maybe looking at a page rank or looking at, the registration date. There's metadata associated with URLs. There's actual data associated with URLs. So it fits well, and that was kind of the appeal to me with this. So as an introduction, I'm going to talk about a description of these things, Then I'm going to get into applying fuzzy to this web phishing. And then I'm going to give you some conclusions and a little more detail on the tooling. And then hopefully, you'll be able, since everything is in Git, and there aren't major promises that I have to make. So, it'll be there. No, it's all there. There'll be some work that you need to do in order to see the example play out in phishing and anti-phishing, but it's there. So we know several types of phishing, right? Most of us have been aware, and it's such a big problem because oftentimes you can't, part of your corporate training includes phishing, right? It includes, monitoring your email, reporting bad links, reporting suspicion. So it's kind of leaked into everyday users where you can't get around it. The corporation can't protect you from it. Where you're just, the solution's not abstracted away from you, right? So that's another kind of reason why I found it useful. But anyway, so these are the types, right? So you've heard of spear and whaling and smishing. And then I have some examples that I gave. Well, we don't have to go through them unless you want to. These are examples, that I had on. So here's a particular interesting email, right? So you download the document. There's a link. You know right away that's going to be a problem, right? This is a text, right? And it's also been in social media where people try to hijack some of the services provided by third-party vendors as well. So it's everywhere. It's all things. And now let me get into a little bit of the fuzzy history. So what's strange is this brings up Aristotle and Plato, where they debated, not necessarily debated, but there was this idea of, it's either this or that. It's nothing in between. And that was Aristotle's proposition. But Plato rejected it, right? Plato was like, oh, there's got to be something in between. You can't just have, it's either green or it's not green, right? So that was kind of, I think, one of the earliest records of this sort of non-crisp logic. Then we move into 1854, where George Boole began, his Boolean algebra. And then almost 100 years later, you get Lochte, Zade. And when I talked about things in March, I mentioned his son, and I'm not going to get into details other than you guys should Google what his son does. He's sort of controversial. Yes, and it'll surprise you what he's done work with. It isn't fuzzy logic. Anyway, so now the cool thing is, we've had lots of work in the 90s on risk, local monitoring, motion control. In the 2000s, we've had network anomaly, intrusion detection. That's kind of when I got in the very late 90s. And then got into reputation, reliability, and trust, and then vehicular, IoT, and resilience. In the, Comcast actually grew up in IoT, mainframe. So I need to say it. So how's this? Something. More glitches. Thanks, Leo. Good. So, anyway, fuzzy really gained prominence. You made a comment earlier, so, I wanted to learn it from back in the. It's been around a very long time, and the difficulty with its adoption, I think it's a simple thing that people. Because you have to bridge together a subject matter expert and someone involved in data science or computation. And a lot of people are smart, right? And But oftentimes they lack that intuition, they lack the heuristics, they don't know the rules, and then you don't bridge them two together. But with other techniques, you can kind of be ignorant about the data, knowledgeable about sort of the patterns of data, right? You could say, oh, I don't know what it is, but I know it's doing something. And there's a little bit of an issue with that with other techniques, like with, say, neural networks. You can determine, a sorting idea to say, here's some silverware, and tell me which group it goes in when I give you some examples. And it'll properly sort, but it can't tell you why. It can't say, oh, there's prongs on this. There's no, or whatever geometric terminology you can use to talk about a surface of something, right? Or the weight. So you got people that specialize in identifying particular metrics, right, that look at appropriately weighted parameters. And there's, right, you've got, I won't say Petri nets, but you have eigenvectors and eigenvalues that rule things out, right? So one of the biggest components, a big property in multi-input systems is linearity, right? And independence. And because if you have independence in a matrix, you can invert it. If you can invert it, you can solve things. You could build a characteristic equation from it. You can get eigenvalues from it. And now you know not just direction, but you get magnitude. So, there's a lot of knowledge you gain about data, but then you still don't know about the problem. You still don't know the ins and outs of the problem. So someone can, if you look at, when I give you the link to Kaggle on the data set for phishing data, you'll see a lot of people about 14 people made contributions that did analytics on the data. And some of the clever stuff was determining against, there's 5,000 phishing examples and 5,000 normal sites. And the interesting thing is people were able to determine what were the important factors. But still those metrics only were important because someone understood there was a subject matter expert on the content. Yeah. So fuzzy suffered, I think, in many ways from that in solving these kind of problems. It flourished in control theory. It flourished in, robotics, right? It flourished in cruise control, basic cruise control. It flourished in refrigeration. It flourished in control systems where they have you ever seen the inverted pendulum problem, right? Where you just imagine, remember ever playing with a broom trying to balance it? That's an inverted pendulum problem. So imagine trying to build a control system that would control the balance of this thing. So that solved a lot of physical problems. But in terms of IT, there wasn't a whole lot of mapping. Like I saw, and there were gaps. Like you saw some work in the early 2010s, and then a few papers that I did see were from like 2018, 2019, and then it kind of spread out a little bit, and then kind of centered around phishing. But rule-based systems and things that have heuristics attached to them, it's very useful. You can get a computational output from kind of rule of thumb, and that's useful. So anyway, that covers some of this history. And in the general case, this is kind of there's a classic example of the restaurant. Has anyone heard of the tipper problem? So you think when you go to a restaurant, right, you're not just gonna flat out tip. You think you do, you may try to, but if the food is horrible, or the service is horrible, or the environment's horrible, it's gonna affect the tip, right? So, but those are fuzzy quantities. It's like, the food was okay, the service, you know when something's bad, but you can't define it. Is it salty? Like, when does it become too salty? You don't know. You just know it was too salty. So on the left is the general case of applying words and terms to assign output based on rules. And in particular, this tipper example is just talking specifically like, well, if the service is poor, then the tip's going to be cheap. If the service is excellent, then the tip is going to be generous. So you have these subjective terms, these fuzzy terms for poor, good, excellent, cheap, average, generous, right? And you could corner people that go, oh, well, you know, what's a cheap tip? And I'm like, well, you know, 10, anything less than 10. So it's like, well, you know, 10.1%, isn't that kind of cheap too? Yeah. All right, so what's it? 10.1, anything less than 10.1? Then you can play games again, right? It's, oh, 10.2. So this exists in many, many ways on how we get by. And there is an element of precision that we want to get to where, you know, how important is it? Do you want somebody, if something's about to come down on you, you want somebody to tell you 1,500 kilogram mass is approaching your head at 45.3? Do you want that, or you want someone just to tell you to look out, right? So to some extent, that's the fuzzy part of it, just the significance of this output. And we have a computing scale that is so great that we don't care anymore to some extent, right? Where it's like, yeah, because I can give a response that's just as effective in, you know, this is a bigger issue than just the words per minute being said. It's more also on the computational part, where we want something kind of fast. We want something responsive. And that's another aspect with fuzzy. You could prototype sooner. It is not the, you know, end all be all silver bullet. For things that you have solutions for, rules of thumb, etc. Like for instance, your example on your research, you could apply this to several methodologies, and you can use these classical methods like the multi-layer perceptron. You can use, you know, Bayesian, right? You could do anything you want. You can any neural architecture and follow that path, and then you can use an inference engine to determine what is the better method, right? Because you have a rule of thumb on how you know what's going to work. And some of it's intuition. Research itself is intuition. From the idea, you have a hypothesis, right? You have a set of hypotheses, and then you have a scientific method that is out to prove the hypothesis so that it becomes some form of a theory, right? And that's your contribution. But that hypothesis is based on a bunch of BS, right? Some intuition, an educated guess, whatever you want to call it. So there's a place in this in many ways. And I've seen it done in weird ways too, where people have made pro-con lists. Like a friend of mine getting a job, he had two choices, and he actually wrote it out, the pros and the cons. And I criticized them. This was 20 plus years ago, and I slowly am getting to the, you know, maybe he was right. If he, you know, he was overwhelmed with with both options as far as like being a stalemate for him that he had to articulate. So that's another thing with problem resolution. All right, thank you. One of our guests. So more fuzzy set examples would be, you know, how do you determine what days belong to the weekend, right? Well, Saturday, Sunday's a weekend, but it's like, you know, Friday after work, that's kind of when the weekend begins for a lot of people, right? So in fuzzy terms, Friday's kind of included, but not for everybody, right? So here you have, this is the concept of weekendness. And the degrees of membership is that 0 to 1 scale. The y-axis is pointing to the degree of membership that it belongs to the weekend. So Saturday, Sunday, bona fide weekend. Although if you have a miserable job, you kind of lose part of that day on Sunday too, because you're just hating knowing that you got to go to work on Monday. So in a way, Sunday night's not your weekend either, because you got to prep, you got whatever for Monday. So that's fuzzy as well. So here you end up with some if you notice, you see Sunday is actually not full membership at 1.0 because of that reason, where, you know, Sundays really suck for people because of it. So here we have, this is a just a more continuous representation of the upper description, the upper plots, the bar graphs for those days. And that's multi-valued membership that we see at the bottom. And the only reason why I have that there is to kind of get you thinking of membership functions. I'm kind of trying to brainwash you a little bit along the way. Do we have any Twitch questions or Twitch feedback?
No,
Go ahead.
so far just Waters is saying, great talk.
Oh, thank you, John.
Maybe it's because I called you Dr. Garcia in the chat. So
Oh, that might...
questions for Dr. Garcia, let's try.
So these are membership functions that now talk about, well, what time of the year are we in? What season? We're in spring, summer, fall, winter, and we know the months, and they do actually have days. So maybe that the feeling for the season is going to be different than the actual label of the day. But we have actual days, and at the stroke of midnight, it's now summer. Unless we could talk about Puxatawny Phil, I guess, for a little bit. So I'm going to go through a few more slides. Bear with me on what this means. The whole thing is all about trying to understand what your inputs are, right? And then you want to fuzzify them. So what I'm doing, I'm giving you examples of what it means to be fuzzy. And once you get that, then there's the rules that you have to play by for fuzzy logic, where you have a mathematical description of a membership function. Keep in mind, it's different than crisp logic. With crisp logic, it's 0 or 1, right? But with fuzzy, it's a transition. It could be somewhere in between 0 and 1. And that's what those curves represent. So for instance, at the bottom one, you could be tall at a certain height. When is someone tall? Go ahead, sorry.
Is there a mathematical function that we apply to make it fuzzy, or is it just like...
There's an operator, it's called a t-norm. There is a function that makes it fuzzy, absolutely. But the actual function I'm describing too, that makes it fun. A membership function is a fuzzy function. It's not crisp. So this is what makes it, when you see the interpretation of I have some value of membership to a state. So to say, I am young with membership 0.01 to the young group, okay? To the young state, to that label of being young. And I might be a 0.8, I'm old. So in Chris' world, it's either you're young or you're old. And it's like, well, if he's not walking with a cane, he's not old. So that's the Chris version, that you're fully a member of that class. You're fully a member of that space. So when you talk about is there a function, yeah, there are a number of functions. You got the way you describe your input, right? You got a way to say, well, I'm looking at the glasses of your frame, the frame of your glasses. They're black. Well, are they pitch black? There's different shades of black, right? So you have different degrees of membership to the state of black, to the color of black. So that transition is fuzzy. And then when you make rules about to say, well, if the glasses are black, and the shirt's black and everything's black, chances are he likes the color black. And that's, you're using a heuristic to determine someone's favorite color. I'm just making this totally up. So those operators, when I just said and, his shirt is black and his pants are black, and his car's black, those are operators, those are logical operators, but they're fuzzy operators. So that's another form of a function of how do I handle two things that have fuzzy membership sets. You with me?
So the fuzzy, so each Boolean condition or rule-based condition might be a mathematical function, and it's the like the aggregation of these Boolean functions that make fuzzy logic, and these functions can be like determined by the experts.
Yeah, close enough. Yes, how you describe the input is from the subject matter expert. How the output's described can be something from the. You still there is an element of domain expertise that plays a role when you're setting this up. Now, this is what I was talking about with the T-norm. The T-norm is a triangular norm, and there are certain axioms associated with this norm. And there are two types. One is just in plain layman's English, you have an AND operator and an OR operator, right? So we got an intersection and a union of this. And these are axioms associated with this important triangular norm that is the basis for fuzzy set theory. And these are just properties. So there is a boundary that's saying that when I take this norm between, any two, like you can apply the same logic of an AND gate, of an AND operator, okay? And if I'm looking at this, I'm basically saying that, well, if both inputs are 0, my output's 0. If I take my arbitrary input and I it's equivalent to the transpose of it. And this is the boundary axiom of the T-norm. And there's 4 of them. So the monotonicity is basically saying that if I do an operator on 2 numbers or 2 sets that are actually smaller than another 2 sets, I do an operator on this, then this operation result is going to be less than this operation result. Vice versa. If it's large, if I take 2 elements in an operation that are larger than another set, then this output should be larger. So when you think about it, it's kind of like saying that I take a set of points, right, and another set of points, and these set of points are just going from 0 to 0.5, right? And I'm now going to manipulate the 2 to say, oh, let me know what's in common with them, or add them up. And then I got another set of points that are larger, that are going from 0.5 to 1. So they're either going to be equal or less than the second set, right? Because this is a set that's larger than this set. You follow? The elements here are going to be larger. That's all this is saying. It's just saying there's a smooth transition with the slope associated. Let's keep the terms correct. With the input sets, if they relate in a decreasing way, the operator on that has to also be less than the other set when it's decreasing. So when it's the set and then the operation of the set. Okay? So these properties, so if you've ever had, have you had real theory or any kind of set theory of real analysis? So, right, you remember when you had to set up a linear space, there are properties associated with a linear space. So, oh, there must be an identity, there must be something called a 0. This is kind of that, I thought of maybe a separate presentation just on the mathematics, but then it totally blows the agenda of it being about security. But that's where you could read up on this T-norm. And there's other sets of connected manifolds of mathematics for this. So this is all I've said. It can't produce an increase in membership value if there's a decrease in membership values. That's the monotonicity axiom. Now, this is a big one where if I do that, it doesn't matter the order of the elements when I operate on it. They must commute. The problem with the order, you'll see that ironically, in control theory, where you have to pay attention to the order of operation, though. Not the order of operation like, oh, multiply, divide, but the order of the elements in an operation. So two matrices, A times B as a matrix does not equal B times A all the time. It's not guaranteed. And the problem with that, often happens where because those properties don't equal, you can end up with different size dimension output, right? So 3 by 2 and a 2 by 3 product is 2 by 3. You can't produce similar elements, similar size matrix. So you already know there's an inequality with commuting. But in this case, it's held and bound to commute. So the operators are different, and that's all I said. So the order of the fuzzy sets to be combined doesn't matter, and that helps in a computational environment like this. So it's like, sometimes it's more efficient to pick how you want to compute things. And if the order doesn't matter, there's an advantage on that. And then the last is the associated property. So I can bring, a T norm on A with a T norm VC, and that's the same as the T norm VC of AB with C, just as I've written it. It's a lot more confusing for me to say it. But anyway, so we can blow past, this is the AND part. Then there's another part, which is the S norm, which is the union of the sets. So we can kind of blow past some of this, but it's the same properties, okay? So these are the CRISP logic tables. Most of you are familiar with them, right? Where we call it out. We got 0 or 1. We know the output for 0 or 1. So in fuzzy, you can see there's other operations that are done on this. You can take the maximum, the minimum, and the inverse, and it is equivalent to the and, the or, and the not. And so for fuzzy sets, since it's an entire set, these are how multi-valued logic takes place. And it's one of the parameters that you use when you describe a fuzzy system. It's like, well, how do I handle an AND? What does an AND mean? Define it. And then these are your options on it. And there's plenty. There are plenty. I won't go into them all, but this is just an example of how you have multi-valued logic in a continuous spectrum for a membership of something. So once again, member of the tall group, he's really a member of the small group and the tall group, but it's to some degree. So the fuzzy process, you start off, there's several steps, and then I'll show you in an example. But you start off with fuzzification of your input, and I have some of these should have gone to, but it's fuzzifying the input. Then you're going to apply the fuzzy operators in step 2. 3 is terminology, right? It's implication, so I should have filled that. Aggregation is the summing of these pieces, and then there's defuzzification. And I have a little blow up. There should be a blow up on some of this. So for input fuzzification, so you can see I got degree of membership. If there's some value I created a variable called personal. It goes from 0 to 1. I say it's 0.3, and now it belongs, or 0.25, it belongs to the median membership function at 0.25. Okay? So that's fuzzifying some value and assigning it to a membership function called median. I could have picked something more fuzzy like, mediocre, something stupid like, J.J. Simpson or something. The thing is, it's about the degree of membership. That's the big key with fuzzy. It's not going to belong to a particular thing. It belongs to everything with some degree of membership. Go ahead.
How do you evaluate whether your fuzzy system is, or are there metrics to evaluate your fuzzy system, or how would you evaluate whether your fuzzy system is set up properly? Is there any parameters you would adjust and stuff like that?
So you have the same techniques that you use in an expert system measurement. So you have precision, recall, you can produce a, confusion matrix. So go ahead.
Just for future questions, could you repeat them just so we catch them?
Oh, yes. So the question was, are there metrics to determine the quality of a fuzzy system? And the answer to that is yes. And you can use the same metrics that you use with expert systems, with machine learning algorithms. So you usually have a ratio of what it got right and what it got wrong, and the type of right and the type of wrong. Meaning, is it a false negative or a false positive, right? Did I get the true positives? Did I get the true negatives? So go ahead. Yeah.
I was wondering what sort of tasks or objectives might a fuzzy system be able to be adapted for, like classification or like regression?
All of it. So for instance, you can use classification. You could build a fuzzy system that says, if all these things are nearly met, then it belongs to class 1. You could build a whole bunch of labels, and it'll still produce, based on the type of fuzzy system it is, you could produce outputs that are integers. And the integers were mapped to classes, right?
I would imagine this would be relatively computationally not very much.
Not necessarily. Computation is going to be based on the amount of rules that are applied, the amount of membership functions, because you have to do these operations on sets. So one of the things in the library that gets set is, how many points do you want to do the computation on? If I say, just like, is MATLAB fresh in your brain still? No? All right, so you remember you could set a range and the step size, right? So imagine if you set the step size to a billionth of a unit, right? And all your sets you're not going to miss a thing. It's covered completely, even though it's a finite set. It's a really, really big finite set. Well, that's going to dictate computation, right? So if you look on GitHub, you'll see I got it set to like 25 points. And it is an empirically determined thing at times to pick the methods of operation, how these membership functions, see how they overlap at the bottom one? That all matters. The top two are triangle membership functions. The bottom are Gaussian membership functions. And you can see there's overlap. So that overlap means that, wow, for one value, I can belong to every set. I'm 0. If I'm somewhere at 0.5, I'm 0 for low. I got some value for medium low. I definitely have a value for medium and medium high, and 0 for high. But I belong to several sets at the same time as one input. So that plays a role. So how you decide to manipulate. Now, there have been automated algorithms that decide on where you choose a membership function style, right? You choose a membership function type. But you could pick where those boundaries are. You could try and make it adaptive. So there are feedback loops. There are fuzzy neural systems. where you determine the weight of a rule. You determine the location of the membership functions, what's optimal based on a training set. So it fits in. The idea with fuzzy is just that you're incorporating human expertise. That's it.
I see. It's more like a framework or a mode of working with information.
Yes, it's one of the easiest ways to take human expertise into a computational thing. Because the other way, like let's take a neural network. Neural network, I can remember, when I worked at a company that built magnets that went into oil wells. And go ahead, Leo.
Sorry, I don't want to derail you. We have a question in the chat. Do you think fuzzy systems belong in the law?
In the LAW?
LAW, yeah, law.
Well, it's honestly, I think it's the same as asking, should software engineers be treated, with the same certification that civil engineers go through? Because it is human for now, right? October's presentation will have the large language model. I think that the further away a human is from that input, I'd say the closer it should be to some legal intervention. And there are standards. That's why there is a standard for fuzzy control. There is a standard. Enough of industry got together and they created a governing body, and there's a fuzzy control language standard. So it's kind of already there. It's maybe self-governing, but if you read it, there is a standard. It is an international standard, and that's what I'm adhering to as the language. So there's a standard on the structure of how you describe a fuzzy system, but the inputs, those details, then it's kind of a broader question, like, should there be a law on creating systems? And that's kind of like what we're facing now. The EU is looking at it, right, with large language models. So, kind of want to say, yeah, go ahead. Oh, sorry.
It seems to me one advantage of this compared to neural nets is it's interpretable. The input is interpretable in the first place.
Yes. But now input for a neural system's interpretable too, right? Because we play enough games, right? There's the null hypothesis, right? We have methods to determine the value of input, and it's not mapped to expertise on the subject, it's mapped to expertise on numbers. So there's some advantage. Where I think it's missing is a neural structure, by looking at it, cannot tell you things about its output, right? There's some heuristic associated. So back to my original story, this magnet, this was 1993, I'm going to date myself. I started taking my first class in neural networks, and I was like, I think I could use it at work. And part of the problem, I would get, they were really smart engineers, and I would ask questions like, what's like a hard problem? I mean, that looks impossible. You built this magnet. Because half the thing in the world is people think that when an oil well is capped, we're done. There's no more oil to pump. That's not true. There's still oil. The problem is it costs so much to get the water out. You got to process more water than to get the oil's worth. So the technique was all about determining where there is a least amount of water and the most amount of oil. And then they used these algorithms like porosity, diffusion, relaxation times to determine, in rock formations and then going down the well, where the oil pockets are. But that wasn't the problem. The problem was they wanted to go 100 feet down and get the exact same answer if they came back the next day. So the repeatability, one of the things, I was a fresh undergrad coming out, And I remembered, like, at the time in the 90s, it was all about digital, gotta go digital. And then some kid from high school, fresh, I had a few years up, he asked me a very kind of common sense question I had to think about. He's like, why digital? Like, why does it matter? And I was like, let me think about it, because I was preaching it without a full grasp of why it mattered. Well, one of the great things with digital is the repeatability, okay? There is a repeatability factor with digital that you don't get without it. Now, with that being said, neural networks, when you do the training and you handle all the data, all the input, all the proper structure, the hidden layer, etc., it's multiply adds that produce this output. It's multiply adds. So if you have the same weight matrix that's going to be applied, you're going to get the same output from the same multiply adds. It's not a dynamically changing thing once it's trained, right? So I gave them that, my own little amateur, way. But the thing is, I ran back to my professor and I asked him, I was like, what is this thing supposed to look at? And I said, I can't get it to work. And he's like, well, you don't have enough neurons in the hidden layer. So he had an expertise on the structure. He knew nothing about what I was doing with the data. And I learned 2 lessons with him. One was the issue of interpolation versus extrapolation. And then there's another part with structure, with the structure of a neural network. And I could see how he was so helpful, and he knew nothing about the nature of the business, right? So my point is that sometimes you can have a massive impact on a solution and know nothing about the data, but everything about its structure, about the structure, not the data of the structure. So he knew rules of thumb, like, well, if you see that you're in a local extreme, like, so when you're training a neural network, eventually the neural network really becomes an optimization problem, okay? So when you look at the optimization problem, it's a multi-state optimization problem. You end up with local extremes. So there are techniques associated with getting rid of those extremes, get rid of the local extremes. I want global extremes. I want to know that those parameters are giving me the minimum output or the maximum output, not just in one little area. And within reason, you can play games to show, like I would do topology graphs that showed the weights moving towards an extreme and getting hung up. And then there are techniques around that too. It's like, oh, you need to change your step size. Or, I don't know if you've ever heard people talk about this. It's like, oh no, your mu is too small. It's taking forever. You need to jump it, and then you got to randomize it sometimes too. So once again, I haven't even got into other things that I've applied, like genetic algorithms, evolutionary computation. There are ways to be a better optimizing solution, okay? And you can incorporate those techniques in a neural structure. Because the goal of the neural structure is that I want to be able to map something to a high degree of multiply adds, a high, just simple linear algebra, and I have a simple baseline computational complexity, right? So it's reachable. I can solve it. So, I like fuzzy systems when there is some knowledge, there's some human expertise, and eventually my argument about quicker, rapid prototyping and computational complexities reduced, etc. Eventually, that's not going to matter. Nobody's going to care. They're going to be like, just throw more GPUs at it. Go ahead.
How if you're going to use fuzzy systems, how much computation might you lessen if you have more a domain input in the different fuzzy logics? Say, if you want to apply fuzzy systems as a blockchain network.
All right, so in a block, I mean, you're picking an interesting example because the concept with blockchain is, right, it's point-to-point encrypted.
It's very important for it to be verifiable and decentralized, but there are certain aspects where consensus can also be sort of fuzzed and like heuristic based.
Well, the new problem becomes monitoring, right? So now you have to have instrumentation in the network to then give you this quality measure, and I would say people might be doing that already with known train sets, and they probably putting a deep learning layer on there. It is. But just in simple terms, because it started off very straightforward. I have some expertise. I'm going to control maybe a boiler system for a power plant, and there's knobs, all kinds of knobs, and tweaking with analog, and you can apply that. Even so, you've taken differential equations. You could build a second order differential equation to describe a shower, right? I got a rate of change on the cold water, rate of change on the hot water, I got a temperature, then I got a time to reach steady state for the hot water, because you're not getting instant hot water, right? So you got knob switching up until steady state for the temperature, and then you have your flow. So it really kind of moved rapidly where everything got blended. Every single, like I said, neurofuzzy, there's genetic algorithms associated with fuzzy rules. It's about like, well, what are the rules? Now I don't even want to know anything. I want this to tell me the rules, because I can bring a data set that can give me my input. I can do some kind of semi-supervised situational. I could build some kind of training set. And in fact, in this example for the Kaggle set, there's 10,000 examples. I looked at ranges so I knew the min and max to put for fuzzy.
How much computation would it decrease? There's lots of research recently to reduce the computation necessary for like these large models and stuff.
Well, the argument has been, say for ChatGPT, the argument has been it's massive, but it's not a problem yet. And 10 years ago, there was an argument about, there were two kind of points about why our quest for human intelligence is an issue. That if we take the approach of trying to be like a brain, it's like you're going to eventually be the size of Texas, the power of Korea, and you just can't get that much silicone to eventually be, right? That was one thing. The other thing is they use the example of why flight took so long. You know why? Because we kept on trying to do things like birds, right? They wanted to build things that flapped. And it was like, no, you got to work on the air pressure differential, and that's going to give you flight. I mean, I'm not going to pretend to be dummies. If they had just asked me, I would have told them no. So my point is that sometimes our observation leads us in the wrong way, in the wrong intuition. And it would mostly make sense to say, well, you want to fly, you fly like the things that fly, right? But no, that held back aviation 100 years or more, from Da Vinci on, right, to the Wright brothers. So we were in that area. I think the only new kind of cool, say, counter to the large language model is it lacks originality, right? There's content that belongs to other people's intellectual property. So that still has to get sorted. I think I will be presenting in October of building an inference engine from a trained large language model. So I'll train it to build the expertise to then tell me what the script looks like. So instead of building, it's writing Python, no, it'll just write a standard fuzzy inference script. And I'm calling it really it's generative AI, but it's really an AI factory. So it's AI producing AI. So the savings on computation, I think it's almost like you insulating a house, really. You find it on the way you describe your input. Is it too much input? How much is noise, right? What is that signal to noise? Then it's like, what rules am I missing? So if you look at MATLAB will give you and it's limited, right? Because you only have 3 dimensions to describe something. So you got to constantly switch the variables to get the new plot. But oftentimes it makes no sense other than you get curvature to talk about coverage of a rule set. And that's why you plot that out. That's because you want to know, out of all these rules, am I covering all the situations? Am I covering it all? So that's another area of optimization. So it's how you fuzzified your input. It's how you describe the fuzzy sets. Are they connected, overlapped? Are they fully disjoint? And then, once you answer the questions on the input and the fuzzification of the input, then you can tweak the other little in-betweens like the aggregation method, the implication method. You could tweak that, but the bigger thing is then going to be in the rule set. So there are ways to try and mathematically derive rules, which you can. You can do that. And people are moving more towards computation and less thinking about the problem. But I don't know. I've been biased towards. I've tried most of them. Right. I've done evolutionary computation, genetic algorithms, neural networks, and fuzzy, and they all have their little roles to play. They really do. So anyway, I've been stuck on this slide. I'm going to blow past some of this. Okay, so let's look at, these are some of the ors, the ands. These are operators. Should I, you know what I'm going to do? Let's look at, this is implication with me. So if I got a rule that the grammar, so on a URL, one of the giveaways is grammar. If everything is misspelled, and the site risk is going to be high if the grammar percentage is wrong, right? So
what if an engineer sent the email?
Well, then he probably fudged something about him.
I can't spell.
Yeah, there's a spell check. So anyway, so here we have grammar percent is low, or the risk site is high. So you have a value for site risk and a value for grammar. You see 0.3 and 0.6. So this particular method of evaluating a rule is called the maximum. So the max between 0.3 and 0.6 is 0.6. Then you have an implication method of, once I know what that actual output of that one particular rule is, what does it mean? So this is a minimum, which is a truncation method. So you can see the graph, right? It's a Gaussian curve that now I've truncated at 0.6. There's another one, which is the product. So I'll end up with a Gaussian curve that's just shrunk to 60% of it. I gotta get something to drink. Everyone, excuse me. What do you have? Do you have any more of those?
Yep.
You do? Cool. Thank you. So these are important, and this is exactly what I said before. So now I take the same value. Thank you. What do we measure? Oh, this is. Thank you. And they're not going to play as big a role in optimizing as tweaking your rules, looking at your inputs, deciding what is input, fuzzifying that input. Do we have any feedback from the chat, from the channel?
John wants to know how you handle snark.
Tell him that I would handle that the same way I handled, what did he ask me way back? What did he ask me? He asked me, can't remember, John. I don't have a comeback for you.
Well, I told him snark was malicious, clearly.
Well,
right?
That and, being snarky is malicious too. So here, I went back to the original types of phishing, and this part is going to really talk about the web phishing that we have. And and this is more about what I've been trying to get through tonight, right? It's like, think about what heuristics exist with the problems that you work on, what the rule sets may need to be. You know, if there's an easier way, use it. I've abandoned ideas, you know, after, like when I first would talk about things at conferences, I don't know, I felt like I had to be almost religious about it. It's like, oh, you know, they should have this in appliances, and, you know, the way they get the sacrament at church should also include this, you know. And eventually you let go, and you need you know, everything looks like a nail and all you have is that hammer, right? And then when it makes sense, you know, you could see insights into other problems. And that's what I'm hoping happens here, that you gain some insight, you play with it a little bit, and you all have some knowledge, and there's some problems I'm sure you want to solve. So if there is a heuristic, you can discover the heuristic, you can learn more now about the problem instead of focusing heavily on the solution. Like you say, oh, I got to do some deep learning. I better get to AWS. I'm going to have to figure out that mechanism, and if I'm at work, I got to handle the authentication issue that is probably a different brand of it. So you hopefully can get to the problem, and there's a lot you can get done without even getting hung up in the tool. So I am going to so this is the part where we can get to the problem, a particular example. How's that sound? Sounds good?
So we have a question from the chat. What is the most complex problem you've applied to fuzzy logic to?
Electrostatic boundary value problems. So I used so there are problems in electrostatics. So basically, it's a differential equation where there is no closed form solution. So you have an approximation. So the problem with the approximation is it's a point-by-point method. So you can use Monte Carlo methods. You can use, you know, any kind of floating random walk, but it's a point-by-point. And then the other is, you know, an Exodus method where you have matrix. So to answer your question, I applied fuzzy to describe the curvature of the solution. So it was a boundary value problem that when you plot the solution out for, say, it's a cross section of hydrocarbons for, I don't know, a little tanker or something.
There it goes.
Oh, nice. What'd you do? Anyway, so I used fuzzy to describe the behavior of a differential equation, basically. And the only reason why I was able to do it is because I solved so many of those problems. I didn't have a closed form solution, but I had a description of what the output should look like. So when you have a boundary value problem, say it's grounded on two ends and it has a potential on, say, the midpoint, your chances are your solutions are going to look like sort of mid-sinusoidal, right? And that's how I described it with a fuzzy inference system. And I did some other stuff. There's some papers I wrote. It probably were things that were complicated in the beginning, and then applying some subject matter expertise to it simplified it. Does that answer? Did that help?
Yeah, so Rogue says interesting. Yes, it does help.
So here is an example of tipping example. And let me give the one. Then I'll demo. So here we have input is going to be service and food, right? We describe our output as a tip. We got now the fuzzification of it. I'm describing what it means to be poor service. I'm describing what it means to be good service. And there are details in how to describe a type of membership function. So I mentioned trapezoidal, or I mentioned triangular, Gaussian. There are a number of different membership functions, and I showed you some shapes of them. So there are just blocks. There's no way around telling you there's no learning curve. There's a little bit of a learning curve on how to describe a fuzzy system using the standard language. This is not Ray Garcia language. This is the fuzzy control language. If you look up FCL, and also when you go to the site and Git, it's part 6 of a multi-part specification that describes the actual language and how you describe a fuzzy system. That is a standard. And how you run that script is up to you. You can use Scholarberry, you can use JFuzzy Logic. There are a few libraries that exist depending on how you want to, slice it. So this is the demo for this particular kind of example. Let me find it in my history. There we go.
Did we anger the demo gods?
No, it should work. It should work. This is also on the site. So here I have 2 fuzzy blocks that I defined, and these are the outputs, but this is describing the membership function for 2 types of inputs. And I have Gaussian, triangular, and if you follow the example that's in Git as well, you will be able to trace where these shapes come from. The demo is what does the plot. When you're actually working in a fuzzy system, you're not plotting everything all the time. It's like trying to write code and putting printf every line. It's not feasible. But this is to give you an idea of shapes, membership function shapes. The example itself will have a rule. So here are the fuzzy rules. If the service is poor, the food is rancid, right? Then the tip is cheap. 3 simple rules to describe it. That's another little piece. Sometimes you get a lot of coverage off of just a small amount of rules, okay? So I encourage you to you need nothing. In fact, in the future, I'll make it even easier where you can get a Docker image and don't have to install anything. It does require you to have Git, so you can pull it, or you can even get a zip file. You don't need Git. But you do need to download SBT. You need the environment to run the application. So there is a hurdle. There is a tiny little thing, and it will change your computer forever. Just, genuflex but if you got a Java environment and Python environment, that's what's been great about, virtual environments, right? You just load up whatever you want. So the plan is to just give you a virtual machine that has it already on there, and when you're done, you can get rid of it. But in Git, you can experiment, and it doesn't take much to actually try these examples. Okay? So let's move to phishing, and then we can roll. So it turns out that there are probably at least 50 different metrics to detect a phishing site, okay? And what I have here are just a handful. And what's interesting is as I looked at a lot of the rules across different publications, a lot of factors were really just Boolean. It's like, oh, is there an ampersand? If there's an ampersand, and chances are it's a phishing site. oh, does it have an iframe in it? If it has an iframe in there, chances are it's a phishing site. So I kept on like looking and reading and adding it in there, and out of 8, what do I have there? 6 belong to Boolean that I don't fuzzify. You can't fuzzify that. So it's like iframe, pop-up window, right-click disabled, fake link in the status bar, an IP address and URL, an @ symbol. Those are just Boolean. So I was like, I started to question the method to go, because there are papers that talk about parsing, just straight up parsing. But there's still value, and there are, if you go to, I have a link. It's, if you just Google Kaggle, has anybody been to Kaggle? All right, so Kaggle and phishing, there's a, and you know what, we can just go there. So check this out. So here we have the data set, but we got 14 contributors that talked about what they did with the data. So if you look at it, you'll see that they parse. Some of them actually read in the data. They, they kind of itemize it, and some do another statistical technique on there. Like this is just looking at the different values associated with them, the quantity of values.
Most of the network data would be text-based and tabular.
What's that?
Most of the network data for cybersecurity is usually tabular and text-based.
Sure. They're here, and it's not any different here. This originated. There's a fish tank. There is, and this is, Kaggle doesn't own this data. This data originated from another research paper that shows you in here anyway. But my only point is to say that this data set, which I found to be kind of the largest really at 10,000 exemplars, had 48 different metrics that they pulled from URLs. And some are legitimate websites and half of them aren't. And it was useful because you can do a whole lot of machine learning algorithms applied to this data. And it makes it useful. And you can measure a fuzzy system against it. So I just kept on reading to get to what inputs are important. So you have URL length that is a quantity. Yes, sorry.
So we have a question from the chat. Would you say that antivirus software uses fuzzy logic?
I don't know. I'm proud to say I don't know. I don't know. Because the thing is that there is some uncertainty, and we've all, I know I've done things where in order to do something in a machine, I can trigger, antivirus software, and it's a false positive. So maybe the fact that it could be wrong doesn't mean it's using fuzzy, but I don't know. I do not know. My understanding at the time was it is signature based, although actually, no, I don't know. I'm gonna stick with I don't know. Because I was started going down another thing with ides and nides and snort, but no. So I don't know. Who asked that question?
Rogue from Stream Chat.
Oh, thank you. Good question. I do not know. So anyway, these quantities, and here's how I basically map most things to either being legit, suspect, right, suspicious, or fishy. And all the outputs can be, oh, it's legit, it's suspicious, it's fishy. I took the Kaggle data set. It's up. Go ahead, Leo.
Can you share the link to that Kaggle data set? Is that in the GitHub?
It is not, but I'm going to. Will it pop up on yours when I text you the link? And then you can put it in the.
Yep. You can just text me it. Or...
there's more, but the Kaggle data set. This is. So I got you started. on something. So I got some simple rules. And basically I'm going, if the URL link is suspicious and the @ symbol exists, meaning it's fishy, then the site quality is fishy. If the @ symbol is fishy, meaning if it exists, and there's a fake link in the status bar, then, so I basically went through all of the single value pieces. And if they all exist, then the site's fishy. And I challenge anybody to test just these 3 rules. Now, the way it's supposed to work is, through Kaggle, you'll get what the right answer is. It's basically training data. It's not training data because you're not applying you're not using the fact that you knew that the input is a site or not, right? So it's not training data for this. But once you have answers from your fuzzy output, you can compare it to the answers what are the true positives and true negatives. And then from there, you could determine the system performance. You should be able to get, the recall and precision off of this. F1 norm, you can, have a party calculating these things. So I'm going to go back to the presentation, and I encourage, I don't challenge you, I encourage you to try these things out. And these were my resources, and I will put up, whenever I get this thing going. So this was from one of the publications, and I will give you the slide. So I do footnote it. The problem with some of these, I pulled some papers from my digital subscriptions. Some papers are actually in the open public domain, and some aren't. So I try to behave, and you'll know once you look up these titles, these references, where they are. Kaggle points to the paper that has the data set and gives you the data set. So that's one thing. The other thing is you could just look at any list. There's in an open internet on what are good rules of thumb on phishing websites, and then you could just look at the 48 different metrics for this data set. There are other data sets. You can go to PhishTank. There's also real-time checks too. Now, part of what is missing in some of the data metrics is that it doesn't, some delve into third-party systems to determine about the domain, right? Is it registered? Is it already a known site? Then the other part, and they show you how to do it as well, and I did not do that here, is to look further into the page. Look at the JavaScript, right? Look at the HTML. There are techniques to regenerate this data, but there are not enough metrics. Even though it's a big data set, and it's probably the best one, there are still other metrics that aren't out here. And the other thing I couldn't find was a proper data dictionary on what the columns actually meant. So some are common sense, but some others I couldn't make sense out of. And then all the rules that I was coming against didn't mention them anyway. So just in my casual, thing across maybe 5 papers, there were about 9 inputs that mattered. So I got you started. The data is on the site, not just Kaggle. I have pre-formatted. I got a script going for you there. I recommend you play with the tipper script just to play, and then all you have to do is modify one of the scripts and just run demo if you want to see what the membership functions look like. If you want to go further and write Scala code, it is a Scala library for fuzzy. But I did not mention that tonight, right? I just talked about it processing FCL standard scripts.
Are there any other programming languages integration for fuzzy logic?
Well, you have MATLAB, you have Java. There is very almost abandoned libraries in Python. I've used Python, so you have at least those languages. The longest, and there's C and C++ too. So and I think Fuzzy Logic was a wrap of the C implementation for Fuzzy Logic. So you can go across the board. What I recommend, because you can still use other languages to integrate with something that's processing the fuzzy part. But if you write for a language, then you're kind of hooked, even though it's multi-platform and you have a different interpreter. If you go with the scripting, the control, the standard fuzzy control language script, it's universal, So you could, in theory, work with PLCs from it.
It's just that there's sort of a programming language for every little technology nowadays.
I mean, look at Kaggle, right? It's all Python, and they handle libraries for data really well. And I mean, personally, I would use that to do the pre-processing, and then you feed in a standard script to the fuzzy control language, and you don't have to use Scala. You can use other libraries that read FCL, but there's some differences. So take a look at what's there that obeys the standard versus the other one that doesn't. Go ahead.
Question from the chat. What are you thinking of applying fuzzy logic to next?
Well, it's more what I'm applying to fuzzy next. So in September, I plan on really moving more towards deep learning, another area of machine learning. But in October, I plan on using fuzzy with large language models. So I want to build an expertise that then, instead of describing a fuzzy system that I did tonight, I want to train a large language model to tell me what the fuzzy system should be. So there's enough expertise, and let it collect it, and then I could show the format based on patterns in how you describe a system. So the application actually is not as significant to me as integrating, just to say Chat GPT with fuzzy generation. So it's really large language models for inference system generation. And this is part of the paper that I cite. These are the conclusions from a paper that I cite. And now, these are methods, and these are heuristics behind the methods and when you use them. So they're not going to improve your system dramatically. These are just rules of thumb on what you set one variable to, what that methodology is. Right, so you can use, just all the main languages to get to fuzzy. And this is the, IEEE Explorer, ACM, ResearchGate, and some are free. Some are free. I use ACM and IEEE Explorer first, and then if I don't find things I'm looking for, I keep searching. That's it. That is all. Any additional questions? Sorry. Are we good?
Yeah, no new questions from the chat, so I think we're good. Who's going to zoom in on that?
Yeah.
Okay, good.
Well, that's how you find me. So, thank you. Thank you all for your time.
And we got one thank you from the chat.
What's this?
We got one thank you from the chat.
Just one?
Well, they're a bunch of ungrateful people.
Tough crowd. I'm gonna close this down.
Should mute that before they riot in the chat.
They're like, yeah. What? We were just being nice. Thank you. You guys hung in there.
And I guess thank you to Iffy Books for hosting.
Yes.
And I will see you next time. We will see you next time. Oh, join us in September.
Yes. There's more.
Good night, all.